Hello, my geometry geniuses. Today we are on lesson 7, unit 4, lesson 7. We're going to actually take our dilations to the next level and talk about similarity. So let's warm up our noggins by discussing the difference between similarity and congruence. So let's look at each one of these diagrams and figure out if the shapes are similar, congruent, or neither. So the first one we have, we got a basketball here, we got a soccer ball, golf ball, baseball. All of those shapes are spheres. And all spheres are similar because they have the same shape, but they're different sizes. The exception to this is the football, because that is in the picture is not a sphere, so it is not similar. So other than the football, all of those spheres are similar to each other. The next one, we've got a couple of cubes. It's hard to tell that they are cubes, but this is an A, B, B, B. So that's how I know they're cubes. It's the same dimension for the length, the width, and the height. So these are similar because they have the same shape but different sizes. Our triangles. We've done some work with triangles earlier in Unit 2. These two triangles are congruent by side, angle, side. Side, angle, side. So they are congruent by side, angle, side congruence. Our two right triangles down here. So in order to tell whether they are similar or congruent, what we need to do is find the missing angle. Right now, I don't have a side length over here to say that it's side angle side, because I don't have this side length as well. There's a couple different ways we could do this. We could find the missing side of the second triangle by Pythagorean theorem. We could do 81 squared plus 50 squared and find c squared and see if it equals 96. If it does equal 96, then they are congruent by side, side, side. The other option is to find the missing angles. So I know that in the triangle on the left, the first one of the angles is 90, because it's marked as a right angle, and the other angle is 58. That would leave me with this angle being 32 degrees. If I did the same calculation with the other triangle, the right angle minus 32 degrees, we get 58. Now, the difference would be whether they are congruent or whether they are similar. Are they the same size? In order to know if they are the same size, I have to finish my Pythagorean theorem. So I have to do 81 squared plus 50 squared. So when I square them and add them, I get 9,061. And then when I square root that answer, I don't get exactly 96. I get 95.189285511. So since they are not the exact same side lengths, but they do have all the equal angles, that means they are similar because they're the same shape but different sizes. So the angle measures match. That makes them the same shape, but the side lengths are different, so they're obviously not the exact same size. So how about the Olsen twins when they were little kids? These are neither. They are not the exact same shape, even though they are twins. Identical twins doesn't mean that they are perfectly identical. And they are not perfectly the same shape, so they are neither. Ha, that was just funny. All right, so we defined two shapes as congruent back when we were talking about congruence in Unit 2. We started off with our transformations and constructions and talked about how if we can map one triangle on top of another triangle through a sequence of constructions, if they are exactly the same, then they will match up with all the corresponding parts being the same angle measure and the corresponding parts being the same side length. Now we're talking about similarity. So a similarity transformation is a composition of a finite number of dilations or basic rigid motions. The basic rigid motions would be your reflection, rotation, and translation, because the rigid motions keep the side lengths the same. The dilation makes it similar because it changes the side lengths, but it keeps the shape the same because the angles stay congruent, but the side lengths change. So if you have a dilation in your composition of transformations, it is no longer a rigid motion. It is a similarity transformation, not a rigid transformation, because it changed size. When we have a situation where we have a dilation or maybe more than one dilation, the scale factor for this similarity transformation is the product of each individual dilations, products of the scale factors of the dilations that occur in the composition. And we talked about this in one of the other lessons. If you do more than one dilation, one after the other, then the overall change in size comes from multiplying each of the different scale factors that were used. So the basic definition for similarity, two figures in a plane are similar if we can find a composition of transformations or a sequence of transformations that maps one shape onto the other shape. Now it can include a size change. So now it's okay that we change the size because that means it was a dilation. It means it's similar to the original, the pre-image, but not congruent. All right, so what I want you to do is pause the video, perform the dilation and rotation. Make sure you're doing it in the correct order, which means you will do your rotation first, and then do the dilation. And then turn the video back on, and we will continue. Now, just to warn you, after you rotate it, your shape will be fine. But then when you do the dilation of 2 on the rotated triangle, point A is going to end up, A double prime is going to end up off your page. Okay? But don't panic. You can still do S and T. So pause the video, do the construction, then come back. So make sure your rotation went in the correct direction. We're doing negative 120 degrees, so it should go clockwise. And now from here, we're going to do a dilation of a scale factor of 2. So as I mentioned, the dilation is going to end up for point A double prime a little bit off your page. But we can see if we have S double prime and T double prime in the right place. So our scale factor of 2 applied to the rotation first. So in order for two shapes to be similar, what has to happen is there has to be a dilation that is part of the mapping of the pre-image onto the image. So when we talked about it in Chapter 2 with congruence, we figured out some sort of transformation, translation, rotation, or reflection, that would map one triangle onto the other. In order for a similarity transformation to occur, there has to be a dilation involved in those transformations. That means there must be a scale factor or a common ratio amongst all the corresponding side lengths. That means everything, all pairs of corresponding sides, have to change by the same scale factor. Using the idea of our scale factor and knowing that all sides have to change using the same scale factor, that's the way we can test to see if two shapes are similar. We can check to see if the ratios are equal between the corresponding sides. So let's try a couple of those just so you can see what I'm talking about. We have rectangle A and rectangle B. We're supposed to explain whether or not the pre-image is similar to the image. So in order to do that, what we can do is check the ratios. If I check the ratio of base to height, it would be 6/2. That would reduce down to 3/1 or 3. If our base to height is in the same ratio for both of these shapes, then they are similar. You could also compare corresponding sides. So I could do the ratio 6/24 and see if it is the same ratio as 2/8. And just like some of the notes we did the other day, we can either cross multiply to see if we end up with the same value, or we could just reduce the fractions to see if we end up with the same value. So either way, no matter which ratios we set up, we see that the ratios are equal. So we can say, because it does say explain, so that means I need words here, ratios of the corresponding sides are equal. So the shapes are similar. And that's what we put for our explanation. So what if we have two triangles on a graph? Well, we can do the same kind of thing. We can take the lengths that we can actually count and compare the ratios. Either the ratios of the lengths between the two triangles or the ratio of the lengths within each triangle. So let's count the base here. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I can drop a height, 1, 2, 3, 4, 5, 6. That is a length of that triangle that I can count, and it does work as a value that I can use. Over here, 1, 2, 3, 4, 5. And the height, 1, 2, 3. I think we can all agree that when I write the ratio of base to base or height to height, we're going to see that they both reduce down to a half. So the ratios are equal. The triangles are similar. So same explanation. The ratio of the corresponding sides and the corresponding heights are equal between the two different shapes, so that means our shapes are similar. So what have we learned? Well, if we have a composition of rigid motions alone, that means no dilation occurs. That means the two figures are congruent. And our symbol for congruent was the equal sign with a tilde over it. Squiggle over the equal sign. If our composition of rigid motions include a dilation, that means the figures are similar. And the symbol for similarity is just the squiggle without the equal sign. If two figures are similar, then there is some sort of transformation that includes the dilation that maps one figure onto the other. And in order for two figures to qualify for similarity, the ratios of their corresponding sides must be equal. All pairs of corresponding sides must have the same ratio. And you have to check all three pairs of sides if you're trying to test if two triangles are similar or not. All right, so let's do some basic algebra remembrance with geometry stuff. Do you remember two supplementary angles? Supplementary. Two supplementary angles are in the ratio of 4 to 5. Find the measure of the smaller angle. Well, one thing that I told you that we should do is take the numbers in the ratio and put an x with each number of the ratio. So the ratio of 4 to 5 actually turns into 4x plus 5x. The 4x and the 5x are supplementary, so that means that they add up to 180 degrees. So the 4 comes the 4 piece of the ratio, the 5x comes from the 5 piece of the ratio, and the 180 comes from the supplementary. So add them together, divide by 9, and we get our answer to the question. All right, nice little review. Cross multiply, solve for k. Do you remember? Not only do you remember how to cross multiply and how to distribute, but once you have an x squared in your equation, do you remember how to factor? Do you remember that you need to get it equal to 0? And once it is set equal to 0, do you remember that you are supposed to find two numbers that multiply to be the number at the end, two values that multiply, in this case, to be negative 30, and they have to add to the number in the middle. So two numbers that multiply to be negative 30 and add to be negative 7. Think about what numbers multiply to be 30. And in order to multiply to be a negative 30, we have to have one positive number and one negative number. Those same two numbers are supposed to add to negative 7. So that would be 3 and negative 10. Once you have your values there, then you know your factors. And then if you had Mrs. Reese, you'll know to do squiggle McWiggle, which means you will set each factor equal to 0 and solve for your two possible answers. This was not a geometric setting, so both answers are totally fine to use in our final result, in our final answer. So k is equal to 10 or k is equal to negative 3. That means there are two values of k that make this original proportion true. All right, some additional properties of proportions. So some of you have asked about this, so let's clarify this. One of the things that I've been stressing is you may have people, some friends of yours, that try to do the same question as you, but start with a different proportion. That's okay. If you have a different proportion, that's okay. What's key is when you cross multiply, you end up with the same result. A times D equals B times C. With that in mind, you can rearrange your proportion, but still end up with the same result. So instead of A over B equals C over D, what if I did A over C equals B over D? Well, if you cross multiply, it's still A times D and B times C. So that proportion, even though it's different from the original, is perfectly fine. What about if I had B over A equals D over C? Again, if I cross multiply, I get B times C, A times D. That's okay. I could keep going with this, but I think you get the idea. Here's the weird one. If you take the original proportion and add the denominator. So if I take A over B and add 1 in the form of B over B, and then take the other side of my proportion, add 1, think about this mathematically. If you have two equal values and you add 1 to both sides, they are still equal. If I change that number 1 into a common denominator with the fraction that's already there, then on the left side it would be B over B. There's the common denominator. Anything divided by itself is still 1. On the other side, it would be D over D, but it's still 1, because any thing divided by itself is still 1, and I needed a common denominator. That gives me, when I combine each side of my equal sign into a single fraction, since they have a common denominator, a plus b over b equals c plus d over d. That one's a little different, but still okay. Okay, so let's practice. Let's practice some of these things. These are some algebra applications. So La Jolla places a mirror between herself and a school building. She places the mirror 60 feet from the base of the school building and 7 feet from her own feet. If La Jolla is 5 feet tall, how tall is the school building into the nearest foot? So this is called indirect measure. We're going to measure the height of the building without actually using a ruler. So La Jolla herself is 5 feet tall. She places the mirror 60 feet from the building. And let's see. And the mirror is 7 feet away from her own feet. We are going to use proportions and similarity to find the height of the building. So how does proportions and similarity here fit into our unit? Well, we have two triangles that are similar triangles because they have the right angle to be equal, and we are using ratio of corresponding sides. So what we're going to do is set up the proportion where we have 5 over 7 for La Jolla's ratio and x over 60 for the building ratio. Then we're going to cross multiply with that. So 60 times 5 is 300. 7 times x is 7. We get this decimal, and then of course we read the directions, and the directions tell us the round to the nearest foot. So that's how we answer the question. All right, a person 5 feet tall casts a shadow 13 feet long. At the same time, a nearby tree casts a shadow that's 28 feet long. Find the height of the tree. So sometimes what helps with this is to draw yourself a diagram. Now your diagram doesn't have to be as amazing as mine. It can be simple and basic as long as you can visualize where the numbers go and how they relate to each other. So a person 5 feet tall has a 13-foot shadow. That makes a right triangle. And then a tree of unknown height has a shadow of 28 feet, makes another right triangle. They are similar because they are happening at the same time of day, so the sun's angles are the same, which means we have equal angles. So now from here, I want you to pause the video, set up the proportion, see if you can solve for the correct x. Okay, so pause it, try it, come back. Now, when you're not told how to round your answer, you have a couple options. Leave all the decimals that the calculator gives you, or round it at the 4th decimal place. So if you're not told how to round it to the 4th decimal place. All right, little Johnny has a shadow that is 3 feet long. He is writing a report for physical education class on tetherball and needs to determine the height of the pole. He knows that he is exactly 4 feet tall with a 3-foot shadow, and he measures the shadow of the pole to be 12 feet long. How tall is the pole? So let's start with our diagram. We got little Johnny, 4 feet tall with a 3-foot shadow, and our tetherball pole has a 12-foot shadow. So there's Johnny and his shadow, and there's the tetherball pole and its shadow. That's creating a couple of triangles for us. 4 feet tall, 3-foot shadow, makes a right triangle. Unknown height of the tetherball pole, 12 feet shadow, makes another right triangle. So I want you to set up your proportion, cross multiply, solve for x, pause it, and I'll see you in a couple seconds. So hopefully you got the height of the tetherball pole to be 16 feet. The Washington Monument in Washington, D.C. is about 556 feet tall. A three-dimensional puzzle of the Washington Monument is 24 inches tall. What is the scale factor used to create the puzzle? Remember, when we are writing ratios to find the scale factor, we always do image length divided by pre-image length. Okay? The Washington Monument came first. The puzzle came second. But we also have to remember that our scale factor has to show a decrease in size from the original to the puzzle. Okay, so with those in mind, we know that 24 inches equals 2 feet because all of our units must match. Trixie, Trixie. So if our monument in real life is 556 feet tall, we either have to convert our monument height into inches or the puzzle height into feet, as long as it's all the same units. So 24 inches is 2 feet, so we can just use that. So that means for every 2 feet of puzzle, there's 556 feet in real life, which reduces down to a scale of 1/278. Part B, using that same scale factor, what would be the size of a 3D puzzle of the Empire State Building, which is 1,454 feet tall? So what we're going to do is take the original height of the Empire State Building, multiply it times our scale factor that we found in Part 4, and then round our answer to the nearest tenth. So if you got a 3D puzzle of the Empire State Building using the same scale factor, you would have a puzzle 5.2 feet tall. That'd be pretty cool. And off you go to practice on your own. Check the answers as you need them. Be safe. See you soon. Take care. Thank you.